Okay, we're going to start. Everything's on tape, so no one can claim ignorance. Um, I guess we can look at finishing up a couple of the examples from the last notes before we start the next notes, and maybe after a few more people filter in, then we'll talk about other logistical sorts of things. Um, so people can always refer to the tape for examples. So we were right at this example last time. We were trying to count the number of factors of 18,000. And so we had just gotten to the point of actually writing down the solution of this, okay? I was using different terminology there, factors or divisors of 18,000. And so the really key to of one way to solve this problem, right, is to think of the prime factorization of 18,000, and that's pretty easy to write down, right? So 18,000 is just 2 times 3 squared times 2 times 10 cubed, right? But then you can further break down 10 as 2 times 5, so it's really 2 to the 4th power times 3 squared times 5 cubed. That's the prime factorization for 18,000. And once you see the prime factorization, then that kind of suggests there the model that you can use to count that number of divisors, okay? So did anybody have who was thinking about the problem last time? We had just about written down the solution, but anyone have a suggestion for what model we can use? What? Use the exponents, right, okay? So the key there is to get a divisor right, you're really going to have to, your divisor can only also consist of factors of 2, 3, and 5, right? That's just the fundamental theorem of arithmetic, okay? So, so really, you could form a divisor as a combination, right, okay? I should use the word combination carefully because we're going to use that term again in this class. It's going to mean something else. But some sort of a product, right, of some numbers of 2s, 3s, and 5s, okay, including 4 2s, 3 2s, and 5 3s, and 3 5s, right, which would give you 18,000 itself, which is a divisor of itself, right? So 18,000 is going to be one of your, part of your answers, right, to this question. All right, so so Dawson says focus on really on the exponents, right, of the, really focus there on the exponents in this prime factorization, and then do what with them? Oh, yeah, just change the exponents, right? Okay, so one divisor, right, would be 2 to the 1st power, 3 to the 0th power, 5 to the 0th power, right? That's just going to be 2, okay, which of course is one of the factors of 18,000, correct, right? So by switching up the exponents, right, okay, in this prime factorization, you can eventually generate all of the factors of the 18,000. So I guess the question is, how many ways can you switch up the exponents? Yeah, Eduardo. So what's your suggestion there? That's correct, right? We want to find different, somehow different sets. Again, I want to kind of avoid the word combination a little bit, but we all understand what you mean, right? Okay, so sort of different sets of the exponents, right, that we could use to build a divisor, right? But what we have to answer, of course, is how many of those different arrangements of the exponents are there, right? Okay, so how do we answer that question, right? So what's our set model going to be, right? To so that we can count how many of those different choices, right, for the exponents on the prime factors we can make. So that's why I'm making the problem harder, right, for you, okay? Because you can probably answer the question but I'm going to make you think about it a little bit more rigorously, right? A little bit more formally. So again, our goal is in these notes is to actually build a set model, right? Okay, that we can count easily, that we can use then as a model, right? Okay, for what you just suggested is I've got to figure out all the different choices, right? I can make for the exponents on the three prime factors, right? Okay, so
Yeah.
so if I phrase it that way, can you continue your answer?
Maybe. Well,
Because we only have a limited number of set models, right? That we've practiced with. Okay, so um, so you really have to choose from the ones that we've discussed, right? So
I guess we have 1M or 3M.
1M or 3Ms.
Like for example.
No, we're only going to have we're only going to have one ultimate model for a D. Okay, so I'm only going to have one ultimate model. I'm hoping we may have to adjust this a little bit, right, to count D properly, but we really only want to have one model for D, right? Okay, but the question is, what is that model going to consist of, right? How are we going to build that model? Um, by the way, look, you've already told me, Eduardo, that or Dalton and Eduardo, you both told me, right, that what's really important here are the exponents, correct, right? Because the prime factors are sort of fixed, right? They're just part of the prime factorization of 18,000. So you can't get a different divisor by changing the prime numbers, right? Those have to stay 2, 3, and 5, right? Okay. But how you can get a different divisor is by choosing different exponents on these prime factors, correct? So for this choice of exponents, which actually corresponds to 18,000, which is a divisor of itself, if you just peel off the exponents and sort of forget about the prime factors, right? If you just peel off the three exponents and look at them, so the first one is 4, second one is 2, right, and the third one is 3, what does that look like? Especially if I put parentheses around it. That looks like a tuple, right? Okay, right. So you can sort of think of your choice of exponents, right, as being a tuple, correct? Okay, with three coordinates in it, right? The exponent for the 2, the exponent for the 3, and the exponent for the 5. Make sure that order is important, correct? Because you know this exponent is going to go with 2, this exponent is going to go with 3, and this exponent is going to go with 5, right? Not a different order, right? Okay, so the order of the coordinates in the tuple is vital, right? That's important to answering the question. But this looks like, if you just peel off the exponents, right, this looks like a tuple. And how do we create tuples, of course? By what set operation? Cross products, right, that's cross products, right. So I'm thinking my set model is going to be a cross product. My set model is going to be a cross product, right? But I have to think of the sets that are going to be in the cross product, right? Okay, so yeah, Eduardo, right. So now that's the sets that you want to define, right?
Yeah.
So what do you want to call those sets?
I guess A, B, C.
That's fine. That's great, right? Or you could call X, Y, Z or really anything you want, right? That's really not all that crucial, correct? So what's A going to be?
0. Oh no, it's 0, 1, 2, 3, 4.
Yeah, sure, right. You can write it down like that. That's fine, okay? And now if it were 0 to 1,000, that would be a little bit harder to write out, correct? Okay, but here's 0, 1, 2, 3, 4. You can also express that in our little bit more sophisticated way. This would be what? The integer segment 4, but that's not enough because that doesn't include 0, right? So you would have to throw in this extra element, right, okay, of the 0. That's kind of the bad thing about these integer segments. They don't have 0 in them, and sometimes we like to have 0 in our sets too, okay? Well, what about B then?
0, 1, 2.
Yeah, 0, 1, 2, right? Okay. So remember A, if we're building a cross product here, and if this is the first thing in the cross product, which I think it's going to be, I think that's what you have in mind, right? This is going to be the first factor in our cross product. Then that has to somehow correspond to the choices for this first coordinate, right? This first coordinate are the possible exponents on the 2, correct? So forgot what I was going to say there. So that's how A came out to be 0, 1, 2, 3, 4, right? So B is going to be 0, 1, and 2. Possible choices for the exponent on the 3, right? And C is going to be What, 0, 1, 2, 3, right? And so you're saying our set model here is what?
Equal to the cross product of.
There you go. A cross B cross C. Yeah. Now, do we know how to count that? So that's a crucial question, because if I can't count this, then I've sort of, that may be a perfectly good set model, but it's, well, when I say perfectly good set model, it may be an accurate set model in that there may be a one-to-one correspondence between these two sets, but it may not be a perfectly good set model, because I may not be able to, if I can't count it, then, it's no better than the original set, right, that I was trying to count. But this I can count, right, because I know how to count cross products, right? So that's that very vital theorem, right? So we know M is going to be what? What's its cardinality going to be? Right, yeah, it's the cardinality of A, right, times the cardinality of B times the cardinality of C, that very fundamental fact. Really, that fact drives really almost, I don't know, 50% of combinatorics is driven by this idea, okay? So many things are related to this. All right, so, but A, of course, is what? 5, and B is 3, right? Or the cardinality of B is 3, and the cardinality of C is 4. So there we have it, right? It looks like there are, what's that number? 60? 4 times 15? So I think there are 60 divisors of 18,000. Okay, yeah. So that's nice. There's that makes 18,000 kind of a useful number because there are lots of numbers that divide into it. So in arithmetic, that makes it a number that we can use a lot. Another number that's like this is 60. Okay, so there are lots of divisors of 60, and of course, 60 is a much smaller number, so it has a lot fewer divisors. But relative to its size, there's lots of divisors of the number 60, and we like that, okay? So that's why the ancient Babylonians decided that they were going to use 60 as a frequent way of measuring quantities, right? So they broke minutes up into 60 seconds, right? Okay, and they broke a circle into 360 degrees, okay? 6 times 60 is 360, right? Okay, because it was easy to do arithmetic with 60 and multiples of 60. They could divide it into parts quite easily, right? Okay. All right, so and that's still with us today. All right, well, anyway, so there's the number of divisors of 18,000. Now, what I'm going to ask you on the test, so we'll talk about the test in a minute, but what I'm going to ask you on the test is to go one step further, right? So you have to explain to me, not that it's not obvious, but you do have to write something down. You have to explain to me why these two things, why this is a model for this one, right? So why is there a correspondence between this set and this set? And the way you do that is just by saying, okay, I'm going to take an element of this set and I'm going to show you how to build a divisor from that. Or vice versa, I'm going to take a divisor and show you how to turn that into a tuple, right? Okay. In this case, it's easier, though, to take the tuple than to pick the divisor. So if I just pick a tuple at random out of this set, right, how does that correspond to a divisor? So you all pick a tuple at random, but don't use one that we've already written down there. Sure, right. Okay, so 3, 1, 2, right? Okay, so that is definitely, I think, an element of M, right? And how does that match up with a one of the divisors of 18,000? So how do you build a divisor of 18,000 from that tuple? What? Yeah, they just become the exponents, right? So this divisor is 2 cubed, right, times 3 to the first power, right, times 5 squared. And what's that equal to, of course? When I say of course, maybe it's not so. What is it? 75 times 8, right? Is that 600? Okay, so that's 600, which is definitely a divisor of 18,000, right? Okay, so we know that is an element of D, right? We know that's an element of D, right? And So you see, that's how you can take a tuple, right, and match that to an element of D. Okay, so that's not a complete proof there of why there's a one-to-one correspondence between these two sets, M and D. That really requires a few more steps, a few more formalities, but I think we can all see it, right? Okay, this is how a tuple matches up with a divisor. So we think, oh, these sets must have the same cardinality, right? Okay, both have cardinality 60. That is one process for counting, okay, right, is using these set models. But again, we're going to talk about another one shortly. There's one other problem here that we didn't finish last time. I thought I would come back to it because I think we can answer it pretty easily. This is, remember, these were strings of alphas and betas and gammas, right? We wanted a string of 7. In other words, we wanted words formed from the Greek letters alpha, beta, and gamma, all right? And we had already mentioned, I think, that the total number of such words that you can form, we also modeled that with a cross product. It's the question A. It was how many words can you form from alpha, beta, gamma, what is it, delta, epsilon, right, from those 5 letters in the Greek? How many words of length 7, I'm sorry, can you form from those first 5 letters of the Greek alphabet? And it was 5 to the 7th power. We modeled that with a cross product also, okay? We modeled that, so that's in the notes. So there's the answer to that. It was 5 to the 7th power right there is the answer. That was the answer to the first part of this question. So the third part here is how many of these total words that we can form from those 5 letters of the Greek alphabet, how many are alphabetically more than alpha, beta, and then 5 gammas, okay? Yeah, Kaylee. So what do you suggest to answer that?
I have more of a question.
Oh, okay.
Suggestion, I don't know.
Mm-hmm.
So the fact that we modeled them, we assigned them each like an integer 1 through 5.
Mm-hmm.
Are we gonna use those numbers as like numeric values to show what's more than other things?
We could. Because, yeah, so when we were answering A, remember, I think we didn't use the set of Greek letters directly, although we're forming words out of those letters, right? But we didn't use the set of those 5 letters. We used instead the integer segment 1 to 5, right? Okay, to represent the 5 Greek letters, okay, and that was a useful representation for the 5 Greek letters because of course the natural order of 1 to 5 we could make that correspond to the alphabetical order, right, of the Greek letters, alpha through epsilon, right, because they have a natural alphabetical ordering as well in Greek, okay. All right, so well, I forgot what your question is, but yes, right. So, so that's sort of correct, right? If you sort of think of this word as a string of numbers instead of this string of letters, the numbers would be what? This would be 1, correct? And this would be 2, and this would be what? Is that 3? Oh, okay, right. So 3, 3. So what is it? Alpha, beta, gamma, delta, epsilon, right? So this is 3, 3, 3. Okay.
Then I guess would you add them all up to be able to say what's more than or less than, or
Well, would you do we even understand what more than means here, right? Okay. Sean, you're shaking your head, so alphabetically more than, right? Okay. So what would it take for a word to be alphabetically more than alpha, beta, and then the 5 gammas, or 1, 2, and then the 5 threes, right?
if you were placing
So in a dictionary, what would get put above this, Sean? When I say above in the dictionary, I mean after in the dictionary, right? So what would it take to? So we could have alpha, beta, and then you said this last one could be what? Delta, right? Or it could be epsilon, right? Okay. Yeah, so if we had alpha, beta, gamma, 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 delta, or alpha, beta, gamma, 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 epsilon, those would be more, alphabetically more, right? Okay. So there's two, so we're up to two. Okay. All right. Yeah, so that's right. Well, we are going to enumerate them, but not one by one. Okay, right? So how can I count this better?
Subtracted that from the max.
Subtracted what from the max?
So 1, 2, and then all threes, our current word from all epsilons will give us the difference between that and the max, right? Which is everything above that. Is that right?
I like the idea of subtraction, but I think you're being a little bit naive about that, right? Okay. So,
Because the first number would just be seven ones. It's not going to be like 0. So you have to know the number between that and
but Sean, let's ask it this way. What would it take there what would it take there for a word to be, uh, what would it take for a word to be more than alpha, beta, and then all the gammas there?
Just have any of the numbers higher. I think I might just be missing something here.
Yeah, no. So try to spell that out a little bit more carefully to me. So how would you get something bigger than alpha, beta, gamma, 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 right? Okay. Can you sort of break that up into some cases for me?
I don't know how simpler to say it. I think like any of those letters need to be one, like the model needs to be one higher, right? So if alpha corresponds to 1, then it needs to be 2. So it'll have to be beta, which is a higher
Oh, okay.
right?
So one thing we could have a beta here, right?
Right.
Okay. Yeah.
I mean, but that corresponds to any of them, right? If any of them is higher, its value is more.
All right. So, but let's start with just let's start there with just beta. Yeah. Hmm.
could you create just like a set of everything bigger when the first letter is alpha, and then everything that starts with beta, everything that starts with gamma, everything that starts with delta, and then have a union of all of them?
Yeah, that's sort of what I'm getting at there, right? Okay, is to try to be a little bit more systematic about it, right? Okay, so so one way to be systematic about it is we know you're going to have a bigger word, right? If you have something bigger than alpha, correct? Right? Okay, and so that would be beta or
Gamma, delta, or epsilon.
yeah, right. Okay, and then what can follow in these six letters, Sean? In that case, if this is something bigger than alpha.
Anything.
Anything, right? Okay. So these can be anything, right? Okay. All right. Now, that's one way, right? Okay, to get something bigger, right? So you can have something bigger here, and then these can be anything. Now, but you also said, oh, I can do something there as well, right? Okay, correct. Okay. So how can you change this to get something bigger?
Gamma, delta, epsilon.
That's right. I can put gamma, delta, epsilon, right? Okay. So how many choices do I have there?
3.
Three, right? Okay. And what about in all of these, though, once you've picked a bigger one here?
Anything.
Anything, right? Okay. All right. And then, but we can also pick what?
Delta or epsilon too.
Right, here, right. Okay. And then what about in these?
Same.
Same, right. Okay. Well, no, wait, what?
Well, no, anything.
Anything there,
Yeah,
right?
yeah,
Okay.
I
All
was
right.
just
All right. So here's a way now of there's a way of kind of dissecting the what we're trying to do, right? Okay. All right. So let's hang on to that idea. All right. So you're off to a good start there. Yeah, Kaylee.
So are we going to do it like we did for the last problem, where we're going to make sets for each individual amount of things, words, whatever, higher than what we already have, and then multiply them together to find out how many more
Maybe. Okay. Right. Maybe we're getting there. All right. So let's come down here. Shall I copy this and shall I see if I can? Whoops. Shall I see if I can just copy this question and bring it down to maybe answer that? All right, so there's the question we answered. All right, so let's make up a name for the big set that we're trying to count, right? So what do y'all want to call that set of words alphabetically more than this string? W again? Okay, all right. So this is words. Um, See why we like to use variable names, right, or letter names, right, for sets, because otherwise we get into having to write things out, right? So words alphabetically more than this, right? Okay, so that's the set we're trying to count. Yeah.
Just to be sure, I think Sean said it. So technically, that set is equal to every single combination of words minus that combination of minus everything up to that set, right?
Okay.
Okay.
I think I know what you're saying. So are you trying to say, Eduardo, that this set is
No,
um,
that's what
this set is all the words, and this set is all the words, and then we take out the words that are less than or equal to this?
yeah, and then subtract it minus
Well,
the
that's
set.
true because that's a set and its complement, right?
Okay.
Okay. So, but you're going in a fundamentally different direction here, okay, than what Sean was suggesting, okay? So you're thinking of I'm going to use a set and its complement as a model. That's another way of going, okay? But Sean, I think, is going in this little bit different direction because he's going to subdivide a W into some other sets, okay? And then what he wants to do is take the union of those sets, okay? All right, so let's see if we can recall now the sets that Sean was using here. So what do y'all want to, so there's several of them, so what names do you want to give them? Um, so we can use letter names or we can use subscripts or A, B, okay? How about just A with a subscript? All right. So I think Sean said first. Well, what did he say first there? Um, Words that begin with something bigger than alpha, right? Okay. Those words are going to be part of W, correct? Right. So words that start with um, what are our choices there? Beta, gamma, delta, epsilon, correct? Right?
Should we say or? Vice versa.
Well, yeah, so this is fine. Okay, right. Because those words are definitely going to be in W, right? Okay. Now, what else here, Sean? So keep going there.
So A2 will be words that start with gamma, delta, epsilon.
No, wait, words that what? It's not words that start with anymore, right?
Oh, yeah,
Okay, words whose what? Second
yeah.
letter is what?
Gamma, delta,
Gamma, delta, epsilon. That's supposed to be a delta. Okay, so that's definitely part of it, right? What else here?
Third letter.
Right, yeah, okay. So words whose third letter would be what?
Everything after.
So that's that delta or epsilon?
Yeah, delta and epsilon.
Oh, okay. And then so forth, right? Oh, I forgot to say. So this is third letter, right? So let me write that down. Is delta or epsilon, right? This is fourth letter, right? And I guess we're going to have to keep going all the way up to, yeah, so do I have to write this down anymore? Let's see. So you get the idea here, right? Except this is fifth, this is sixth, and this is seventh. Okay, so, yeah, right? I think all of these, I think you're right, right? All of these sets, correct, okay, are certainly subsets of W. And I think if you take the union of all of these sets, right, that's going to give you all of these words, right? Because I don't think there's any other situation, right, where you can have a word more than these, okay? All right, so you've got that much right, Sean, okay? So this is a good start. So we know that W here is A1, union A2, union A3, right, up to A7, okay? Oh, this is, yeah, that's right. But now you want to count W, correct? Okay, so what sort of model here is this called, Sean? What sort of thing is this that you've sort of proposed for counting W? Think back to our models. So here we've gotten this set W. We've got it written as a union of a bunch of sets, right? What's that called when you take a set and you've got it broken down into a collection of subsets? Begins with a P. Partition. Right, that's a partition. So what you proposed here is, I've got a partition of my set W, correct? Right? I've got a partition of my set W, okay? Because I've got it broken up into these subsets. So I know something about counting partitions, right? How does the cardinality of your set match the cardinality of your partition? If everything is like it's supposed to be, what should be the case here? Yeah, it should be we should be able to add up, right, the cardinality of the part. So see, you've done this really nicely, or I think you've got it started really nicely here, right? Okay. But we have a problem because this is not really a partition, Sean, unfortunately. Because what has to be the case in a partition? What now?
Doesn't there have to be only one occurrence in each? There can't be.
Yeah, there cannot be what?
No, there can't be. They have to be disjoint.
They have to be disjoint, right? They have to be disjoint. Okay. So to really get a partition, your parts, these are called parts, right? They really have to be disjoint. Okay. Are these parts disjoint?
If we slightly adjust the set.
But not now, right? Okay. Because Sean, why not disjoint? Look at A1 and A2. What's the problem there? I think even those two parts are not disjoint, right? Can you think of a word that's in both of those? So A1 starts with beta, or gamma, or delta, or epsilon, and A2 is just the second letter has to be gamma, delta, or epsilon. So can you write down a word that's in both of those parts? Well, it's got to be in A1, right? So what does it have to start with? No, it's got to be an A1. What? You got to start with one of those things, right? So if you have a word that starts with beta, correct, but can it also fall in A2? Because A2 just says what? The second letter has to be what? So the second letter has to be gamma, correct? Right? And then we don't care about the other 5 letters, right? Okay? So if we want to, we could make those all epsilons, right? That falls into both of those, correct? Because it meets your description of both of them. By the way, that is alphabetically more than, right? Okay? So that is in the set W, but so it is in the set W like we wanted. But unfortunately, that string is in both A1 and A2. So these are not disjoint. They're not disjoint. So it ruins the counting, see? Okay? Because we don't know yet how to count unions that are not disjoint. But we're going to learn that, okay? We're going to learn that, and that is related to what theorem? So what theorem allows us to count unions? What was that theorem called? We had a theorem about unions. What? Inclusion, exclusion. So, but remember, our version of inclusion, exclusion was kind of restricted. It was to 2 disjoint sets. Well, it was the union of 2 disjoint sets. So we have a union here, but unfortunately not even disjoint. But we're going to extend inclusion, exclusion so that it will account for how to count unions that are not disjoint. But we haven't gotten there yet, right? Okay, so I'm in trouble, but I can fix it. Because what do I want to do to the parts? Make them disjoint, right? Okay, so how can we make them disjoint? Okay, so how can you go back and adjust that? It's going to be hard to write in words, but how can we go back and adjust that so that we make them disjoint? Yeah, Kaylee?
I just wanted to ask, since that word is going to be in all 7 sets, for the inclusion exclusion thing, do you just have to focus on 2?
Do I just have to focus on what?
2 sets. Like you were focusing on A1 and A2, but could you
No,
write with all 7 at once?
Once I think to answer your question, once I have focused on A1 and A2 and fixed that problem, I think the others will sort of fall into place. You'll see how we can fix the whole thing. Because it's the same idea. We have to apply it differently, but it'll be the same idea to make them all disjoint. Okay? All right? Okay? So how can I get the first 2 separate at least? The first 2 separate. What's the problem with, what's really the problem here? Yeah, it's the fact that A2 can start with beta, right? Okay. See, Sean, the idea of A2, right, of that set of things in A2, right, was you wanted the second letter to be higher than beta, correct? Right? Yeah, correct. You wanted this. That was really the key thing, right? So what you can do is say for A2, right? Let's assume that we make the beta higher, but we keep the alpha. See, we keep the alpha, right? Because if the alpha is the same, but the beta is higher, we'll have a bigger word, right? So that it was really the key thing there was really changing beta to something bigger than beta. So that's how we're going to fix A2, okay? A1 will just leave the same. Anything that starts with something higher than alpha, beta, gamma, delta, or epsilon, we'll leave that in A1, okay? But A2, we're going to modify its description. The second letter is going to be this, right? But the first letter will be what? Keep what? Ah, right. But first letter is alpha. So fix the alpha, you see, okay? And then just form words that start with alpha, but the second letter is really the higher one, right? Or the subsequent letters can be higher too, okay? Right? Okay. Now you see the trick here? Now, do A1 and A2 overlap now? No. Okay, why not? Because A1 has to start with what? Yeah, one of these. Cannot start with alpha, right? Okay? Cannot start with alpha, right? Okay? All right. Now, how do we fix A3? That's right. So keep the original letters in the word, right, but up the third letter, correct? Right? Okay? All right. So So how do I describe that, Sean? This third letter is this, but first two letters are what? Keep the first two letters. What were the first two letters I was going to keep? Alpha, beta, right? So the first two letters are alpha, beta. What about this one? A4. Fourth letter is this, but what? Yeah, but first three letters, right, are alpha, beta, gamma. What is it? Alpha, beta, gamma. See that right? Okay. So this and this cannot, well, this cannot overlap with any of the previous sets, right? This one can't overlap with the first set because its first letter is alpha, but this says the first letter is not alpha, right? This one, the second letter is beta, but this says the second letter cannot be beta, right? Okay. This says the third letter is gamma, but this says, what does it say there? Okay, right? Oh, no. This says the third letter is bigger than, right? Than gamma, correct? So you have now, if you continue that, you've got to continue that same pattern, right? You will have disjoint sets. How do you describe the last one? So the seventh letter is these two, right? But what's the same here from the original string? The first six letters, right? Okay. So the first, what? Yeah, all right, sorry. So the first six letters are, got to spell this out, alpha, beta, gamma, 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 gamma. Okay, right? Now you have a partition because now the sets are disjoint. Does everyone understand that the sets are disjoint now? Okay, right, because of the way we've defined them. So that's really important. The sets must be disjoint because otherwise this theorem is not going to apply and we have no way of counting them. But now we still have a counting problem ahead of us because what do we have to now count individually? A1 through A7, right, okay? So now we have to count A1 through A7. But I think you can do this really quickly now, okay? Without, we're not going to go through writing down our set models for A1 through A7. We can, but they're all going to be cross products, all right? But so I think we can immediately see what their size is going to be. What's the size of A1 going to be? Okay? So what do you know about A1? It starts with what? It starts with four options, right? Okay, so you have four options to start with, right? So if you want to model A1, you would start with you would use a cross product, but how big would the first set in the cross product be? Because how many options do you have for your first letter? Four, not five, okay? Right, four, not five. Because you're excluding alpha, right? Now, what about for the other six letters in the strings in A1? How many choices do you have for those other six letters? What? Five, right, okay? So altogether there, in my cross product, if I model A1, I will have a 4-element set, right, times a what? There you go, right, okay? So the cardinality of A1 must be what? 4 times what? 5 to the 6th, right, okay? 4 times 5 to the 6th. What is A2 going to be? What now? 3 times 5 to the 5th, is that right? Oh, that's right. So in the alpha is fixed, right? Okay, so no choices there, right? In the second letter, you have 3 choices, right? And then 5 for the remaining 5 letters, right? So this is 3 times 5 to the 5th power, right? Let's see. All right, what's the third one here? I think we have to write that one down at least. What? 2 times 5 to the 4th, right? Okay. What's the next one? 2 times 5 cubed, right? Plus 2 times 5 squared. Plus 2 times 5. Did I get them all? Is that it? No, I'm missing one, right?
Yeah, plus 5.
Isn't there just a 2 here at the end?
Uh,
How big is this one?
oh yeah,
Yeah,
yeah. Plus 5 to the 0.
yeah. 2 times 5 to the 0th power, right? Okay. Don't forget this set, right? That set only has 2 words in it because the first 6 letters are fixed. What can go in the last letter here then? Yeah, delta or epsilon, right? So there's only 2 words to finish this up, right? This set. Oh, so you have 2. It is a pattern here. You can think of that as 5 to the 0th power, okay? All right. Ah, there it is. I'm not going to add all those up, okay? Wow, we really went about that the hard way. I encourage you to think of it as a complement. I think you can do it a little bit shorter. It'll still take some thought, but think of it as a complement. So what would the complement be? I'm not going to count the complement, but if I say think of this as a complement, here's what I mean. We want the words, right, alphabetically more than this string, correct? So the complement of that, of course, is words what? Less than or equal to, right? Less than or equal to. What was that string again? Alpha, beta, and then a bunch of gammas? Yeah, okay. Less than or equal to that, right? That's the complement. And so we know how to count W, right? Okay. W is going to be, of course, the universal set minus the size of the complement. But what is the universal set? That was this original set that we counted here, right? That we called S. And remember, that was the set of all possible words of length 7 from those 5 letters. And remember, we counted that was 5 to the 7th. So I know what to fill in part. I know how to fill in part of this, right? Okay. There's the universal set minus this, but this is 5 to the 7th. So what you can count W if you can count the complement, right? Now you might say, well, it's got to, I mean, isn't this just as hard as, isn't W bar just as hard as W? I mean, is it, words less than or equal to this, aren't they just as hard to count as words greater than this? Well, you're going to use a similar idea, but I don't think it turns out to be quite as hard. You can make a partition with fewer sets to count the complement, okay? Just think of sort of this scheme backwards, all right? Think about what has to be in these letters, okay, right? Well, nothing can go here, right? Because alpha is the first letter, correct, okay? So that choice is already, you don't have to worry about any choices there, right? Okay? You just have to get something what? Smaller there, right? How many choices, though, are smaller than beta? Only 1. See, so that's sounding better already, right? Okay, and then not too many choices, also less than gamma, right? Okay, so so it might be easier to count the complement here, and then subtract it from 5 to the 7th than to count the original set. But you'll use the same idea, it just won't come out to be so bad. Okay, so many sets in your partition, I think. All right, so try it that way. Oh, you got it? Is there really a number there? Is that it? 73? What is it? That's this set? Where did I count that? So 73,000 what? 437. We'll have to trust you because I doubt if anybody else did those calculations, Kaylee. So until somebody challenges Kaylee, she's got to be correct, right? Okay. So 73,437. Exactly. Nice problem. Beautiful problem. Demonstrates really almost every single, well, it does, I think. Every single model that we've seen so far, I think, came up in this very problem, right? So we had cross products, complements, if you want to go that direction, partitions. We didn't quite we didn't quite have a union of two disjoint sets, but of course a partition is just a union of multiple disjoint sets, right? So a union of two is just a simpler version of a partition. Yeah.
Um, sorry, just to like kind of conceptualize it better, can you?
How could it possibly be conceptualized more than this?
For example, what would be a letter in A2 after you put the restriction that it has to start with alpha?
What would be a word in A2?
A word in A2.
What would be well? Can we just write one down?
Alpha and all gamma.
So it's got to start with alpha, right? Okay. But the second letter has to be one of these, right? So it could be gamma, and then it doesn't make any restrictions on the later letters, right? So these could all be epsilons, just like here, right?
So after the restriction, A2 is no longer greater than A1?
After I don't know about greater. It is greater, right?
Oh, no, like the other letters don't have to, but
Oh yeah, it's not greater. Yeah, you're right.
beta is.
Right. It's not the words in A2 are not bigger than the words in A1, but the words in A2 are bigger than alpha, beta, gamma, 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 gamma. It's another way of being bigger than alpha, beta, gamma, 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 gamma. Right? Okay. Sounds like a fraternity gone mad there, right? Go ahead. What?
So should we mark this particular problem as like something that will be on the test?
If there's something like this on the test review, then yes, right? So,
There's something like A and B.
there is something like that, right? So I don't think it's quite as bad as this one, though. I don't think any of there probably there are probably questions about strings and strings more than something, or strings end and start with something, right? So there are going to be string questions for sure, word questions, right, like this. Okay, all right. Listen, we have to get a little bit further in the notes here. Wow, that was one. This is okay. So this is a famous thing about combinatorics. So there's a famous quote about combinatorics from a famous mathematician. There's a movie about him, by the way, and forgot the name of the movie. I'll remember it. You can probably find it on YouTube. But his quote is, in combinatorics, any fool can pose a question that the wisest man cannot answer. And that's what makes combinatorics so fun. Is it's very easy to pose questions, and sometimes even simple questions can be very difficult. All right, so. But I have lots of examples in the notes that we still have to talk about, and they're all related, but they're all slightly different. And that's also the fun thing about combinatorics. Each problem is kind of its own little puzzle. All right. Okay. So finally, we're finished with these notes. So, but now we're going to talk about a different way of modeling sets, and this is using algorithms. So, or a different way of modeling sets or counting sets, but this is using the notion of algorithms to create elements in the set. So you're probably more familiar with this idea than you are with set models, okay? And so you might find this easier. But in the long run, we're going to end up mixing, for complex problems, we're going to end up mixing the two techniques. They kind of always go back and forth. You'll have models, but you'll intermix that with, you'll build a model to count a set, but then you'll intermix that with some algorithm for creating elements in the set. There's a subtle interplay between these two techniques, okay? All right, so I'm going to write down I'm just going to state some facts about algorithms, and I'm not sure if I stated these correctly, but formally correctly, but you'll get the idea of how to apply these. They may be pseudo-theorems the way I've stated them. All right, so suppose you have an algorithm, or you can think of it as a computer program, right? And suppose it has a branching point in it, right? So a branching point in a program, right, is like an if then else, right? So it's where you've got where you have alternative sequences of executions, right? Now, in 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 basic programming, you'll have an if, then, and an else. So you'll have two sequences of executions. But in all programming languages, you have branching statements where you can have multiple sequences of executions, right? So, and I think in C++, that would be a case statement, correct? So a case statement is just a kind of a souped up version of an if then else statement in C++. Or is that, am I thinking Pascal? So anyway, all right. So that's just kind of all the background there, all right? So suppose you have an algorithm, a program that has a branching point, and suppose there are, this is a small p. So suppose there are P1 paths of execution following one branch from P. I'm pretending there's just two branches, but there could be multiple branches, in which case you can just extend this to multiple cases. And P2 paths of execution following the other branch, okay? Right? So you come to a branching statement in your program, right? And if you take one branch, there are P1 paths of execution from that branch. You follow another branch, there's P2 paths of execution to the end of the program from the second branch, right? Well, then how many paths of execution do you have altogether for your entire program before it reaches termination? Well, that's obvious. It's just P1 plus P2, right? Okay. I mean, if you go this direction in your program, there's P1 ways of reaching the end of the program. If you go this direction, there's P2 ways of reaching the end of the program or the end of the algorithm. So altogether, you have P1 plus P2 ways of reaching the end of the program. Okay. Duh, right? So there's nothing mysterious about that. Now, how do we apply that to a counting problem? This is not going to be a profound application, okay? Because this is not a profound theorem. The next theorem is more interesting, but let me show you. So we're going to go back to a problem that we answered earlier, okay? So suppose our well, not suppose, right? Our class consists of 12 math majors, 2 math teaching majors, blah, 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 right? Just like before, okay? And I want to know how many students are on the class roll, okay? So I want to answer that question. All right, so obviously it's 20, right? But how do we apply that theorem to arrive at the answer of 20? So in a sense, when you are coming up with, I claim, in your mind, somewhere in your subconscious, when you are answering this question saying, oh, there's 20, you are, in a sense, executing an algorithm in your mind to do that counting for you. And I claim that algorithm sort of corresponds to this theorem. Let me make it, but the way to show that correspondence is to let's make the problem a little bit more detailed here. Suppose that we have got the majors segregated, okay? So the 12 math majors are in one room, okay? And the 2 math teaching majors are in a separate room, right? And so forth, right? The computer science majors are in another room isolated, right? Okay? So we have broken out all of the different majors into different rooms. And if I ask you, what's an algorithm? What would be an algorithm for selecting a single student from the class? How would you describe that algorithm? So if I ask you what's a step-by-step process, right? An algorithm for selecting a student from the class, what would that algorithm be? So keep in mind, right, that we've got the majors, as I said, they're segregated into different rooms, okay? So they're separate from each other. So if I said, describe me a process for picking someone out of the class, what would that be?
There's no double major, right?
Yeah, no double majors. Yeah, we've excluded double majors. We really don't want to, because then we're going to have to start doing, partitions and unions, and I know that's really got y'all befuddled, so I'm going to simplify. I'm sorry, I'm insulting y'all here, but I'm really just teasing you. Okay, all right, so Eduardo, since you spoke, then you have to give me an algorithm. So what would be an algorithm? If I said, go pick a student from the class, what choices would you have to make?
I would have, how many students do you have? You have 20 students in the
Yeah, no, so describe what you would do, just in very elementary terms. If I said, go pick a student from the class, what would you do?
I would
Just tell me what you would do, right?
go into the class.
No, you cannot go into the class because I said they are in different rooms. Right, see? Okay.
I would arbitrarily pick one of the students.
That's not how you would start. No, what would he have to do first? He would have to pick one of the rooms, right, okay? You would have to pick one of the rooms to go into, right, okay? Yes, right, correct? Yeah, all right. So look, now there is your branching point in your algorithm, right, okay? You have to pick a room, right? You have to pick a room, okay? So you have a branching point here in your algorithm for selecting a student, right? Because you got to pick a room, and you're going to have different executions, different sequences of executions from that branching point, right? Okay. So first, you have to pick a room. How many branches are there from that branching point? So how many different paths of execution are there from that branching point? What?
Can there be more than two?
More than two what? Oh yeah, there can be more than two. Yeah, that's what I was trying to say. That theorem is stated for two branches from a branching point, but there can be multiple branches from a branching point. Yeah. Five, right. Okay, is it five? Yeah. Okay, 1, 2. Yeah, right. Okay, so 5. Yeah, so you've got to make a choice of rooms, right? Then, once you've made a choice of rooms, what do you do? Then you can pick a student. That's right, okay? So then you can go in and pick a student, right? Okay? All right, but the number of choices depends on what?
Respective to the class. So if I go into math class, would I have 12 choices?
You have 12 choices, right? So the number of choices depends on which room that you picked, right?
Yes,
So you see, you have different sequences of execution based on your the choice of the classroom, right? Okay. So if you make if you follow the first branch, which we will say is you go into the math major classroom, then how many ways do you have of finishing the program? 12, right? Okay, right? Okay, because there are 12 choices you can make there, right? Okay. If you go into the math teaching room, you have 2, right? Okay. If you go into the computer science room, right, you have what? 3 passive execution, right? Okay, because there's 3 people you can pick. So you see, the passive execution depend on your first initial choice, right? It depends on that branching point, which classroom that you choose. Okay, so altogether, how many ways do you have of finishing the algorithm, of picking a student? It's going to be what? Sure, right, which adds up to 20, right, okay? So you see, that's how we know that there are 20 altogether students in the class, right, okay? Based on the number of ways we can execute that algorithm. And we know the number of ways we can execute that algorithm based on that theorem, right? Okay, I mean, formally, we know based on that theorem. I know you know this easily, right, without thinking about that theorem, but I'm trying to, again, make it a little bit more formal. Yeah.
So if we're looking at it like a graph, then
Oh, yeah, so you can look at it like a tree, right?
mm-hmm.
We often,
So
yeah, so we often model programs with trees, right, with flowcharts, correct, right? And,
So each of the 5 branches
right, yeah, corresponds to a choice of a classroom, right, okay?
and each of those
Has a certain number of, that's right, yeah, exactly right.
Okay.
Perfect, right. Actually, drawing that picture is informative, so I should have put that in the notes, okay? I may come back and put that later, but I don't want to put it right now because we're running out of time. I want to show you the next theorem, though, because this theorem is very simple, right? That seems almost too trivial to be, really meaningful to us. But it leads to a really important theorem that is really helpful, okay? Now, so suppose you have an algorithm that has a sequence of branch points, but they're in sequence, right? Okay, so it's not, just a single branch point, right? But we have a sequence of branch points, right? So you have an if-then-else followed by another if-then-else followed by another if-then-else, right? Okay, in your program. That's frequently, of course, the way programs actually work, right? They're not just, one branch point, right? Usually have multiple branch points, and they're in sequence, right? Okay, all right. So suppose you have an algorithm with a sequence of branch points. I'm labeled them P1 through Pn, right? Okay, and then we know that, so if you take, so in your first branch point, right? Okay, there are P1 paths of execution following that first branch point, right? And then there are P2 paths of execution following the second branch point, correct, right? But remember, these are in sequence. These are in sequence, right? This branch point, and then we have to make this choice after we made this choice, right? And then we have to make this choice after we made this choice, right? And so on and so forth. So you have a sequence of choices, okay? But it's really important here, really, really important, right? Okay, that you got to read this, okay? There are always P1 passive execution after the first branch point. Okay, so it doesn't matter the choice you make at your first branch point. There are always this many passive execution following that. Y'all understand that, right? Okay, the number of passive execution does not depend on what choice you make at the first branch point, and so on and so forth. Okay, then how many ways do we have to execute the program altogether? It's just going to be the product of that number. Of those, a number of executions after each branch point. Just take the product there. Okay. That you're not going to understand that theorem until we actually apply it, right? But it's very easy to apply. So let's go back to picking a team from a class, but I'm going to make it a little bit difficult, a little bit different problem. So suppose we want to pick a team of 5 officers from our class, right? Okay. How many such teams are possible? Okay. So we're not just picking a team of 5 equal team members, right? Okay. Each person that we pick on the team is going to have a particular rank, right? Okay. So we have to build a team that way. All right. Can you all describe for me now an algorithm for building the team? So what's an algorithm for building the team? Who have I not called on? I don't know your name. What's your name?
Trey.
Huh?
Trey.
Trey? Yeah, what's your major, Trey? Math. Okay, so Trey, you're a math major. So this is a question about algorithms, but algorithms are important to math too, not just computer science. So so can you just describe for me that process, right, for creating this team? So you've got the 20 people in the class, right? How would you go about forming this team? But remember that you're picking members of the team. There's going to be 5 of them, but remember they're assigned to specific ranks, right? So how would you go about building that team? What would you do first there to create a team? I know if I gave you this task, just said, I need you to create a team for me of 5 officers of different ranks from the class, right? Go create the team. I know you could do that. So just how would you do that? Just you said it there. So just don't be shy. What? Just pick a person, right? Okay. But what are you going to do with that person once you pick them? Assign them a rank, right? Okay. So you're going to pick a person to assign a rank, right? Okay. All right. So so let's put our ranks down there, right? So here is, I don't know what these ranks are, right? So I just got to give them sort of arbitrary names, right? Okay. So you said I'm just going to pick a person, right? To, oops, this is rank 4, right? So I'm just going to pick a person, right? And to assign to my first rank. So how many people can you pick there? Because we're just doing this arbitrarily, right? So we're not giving him a quiz or something to decide who would be the best person for this rank. We're just doing it arbitrarily. So how many choices do you have there? 20, right, because we just answered that in the previous problem, right? Okay, so you see, there's the first branching point in your algorithm, right? Okay, you have to pick the person for rank 1, right? Okay, you have to, so you've got 20 ways of making that choice, okay? Right. Now, look, Trey, this is really important, all right, because what are you going to do next, of course? You're going to pick another person, right? Okay. So you see, you've got a sequence of choices here, right? That you have to make because first you picked rank 1, correct? Okay, and then you picked rank 2, right? So you see, you're doing this in sequence, right? Okay. Now, so you've got 20 ways of picking rank 1, right? So there are 20 paths of execution there at that branch point, right? Now, after you've picked rank 1, though, how many ways can you pick rank 2? 19, right? It's 19, see, okay? So for your second branch point, you've got 19 paths of execution, right? Okay? So this number is the number of choices here. The number of ways of making that second choice is 19. Notice that does not depend at all on that's always 19, right? Because it doesn't depend on which choice you actually made for rank 1. It does not depend on the person you actually chose for rank 1, correct, right? So you could have picked Taylor, or you could have picked Dalton, or you could have picked Sean. That wouldn't have made it any difference at all. You would still had 19 choices here. That's really important, okay, right? So the number of paths of execution here the number of choices here cannot depend on, it's always got to be the same, no matter what choice we make here. If it's not the same, then this theorem doesn't apply. We're going to see situations where it's not the same. How many here? 18. See, now you're down to 18, right? And how many here? 17, right? Okay. And how many here? 16, right? When you finish that algorithm, what are you going to have? A what? You're going to have a team, right? Okay, of 5 officers, correct? You're going to have a team of 5 officers, right? See, that's what that algorithm produces for you, is a team of 5 officers, right? Okay, so you see, there's our algorithm for building the team. Now, how many ways are there to execute that algorithm? Now we know, right? It's what? It's 20 times 19 times 18 times 17 times 16, right? That's what the theorem says, right? When you have a sequence of choices, then the number of ways to make that sequence of choices is going to be the product of the number of choices you have, right, at each branch point, correct, right? At each choice point. So, I didn't write down is this our set of 5 officers, right? So there's our set of 5 officers, and so we know, right, that the size of T is 20 times 19 times 18 times 17 times 16, whatever that number is, okay? Because that's the number of ways that you can execute the algorithm to build the team, right? So you see so I don't have a set model here anymore, right? Well, I kind of do have a set model. My set model is the number of ways of executing the algorithm, okay? That's really the set model. But we're not going to make that quite explicit here. We're simply going to say, I have an algorithm, right, for building a team, and then we have some tools that can help us count how many ways there are of executing that algorithm. Be sure, by the way, when you think of your algorithm, so what we're doing is we have an algorithm for building an element in the set that we're interested in, and we're trying to count the ways of executing the algorithm. We have to be careful about one thing, though. Make sure that your algorithm does what? See, we want an algorithm for building the team of officers, so we have to make sure that the algorithm actually does that, right? Okay, we have to make sure that at the end of the algorithm you have a team of officers. If you have something different, then that's not the right algorithm, correct? Right? Okay, you have to have an algorithm for building the element in the set that you're interested in, and you must be careful that you don't have an algorithm that duplicates items in your set. So if you have an algorithm that builds something in your set, but there are different ways of executing the algorithm to get the same element in the set, then you're in trouble, okay? You can build a set with the algorithm, but you won't be able to count the set by thinking of the algorithm. Make sure that when you execute the algorithm, different executions of the algorithm give you different element of your set, okay? Usually that will be the case, but there may be several instances where that's not true, okay? All right, y'all see the algorithm? So we just picked the rank 1 person, we picked the rank 2 person, etc., right? Okay? That's how we got the team. So this is how I know how many are in the team. I do not. Do y'all know us? I don't know a set model for yet. I don't know a set model for this set. Okay, this is not a Cartesian. Well, it is a Cartesian product, but it's kind of a subtle Cartesian product. Okay, so I shouldn't say that I don't. I do know a set model, but it's hard to think of what the set is. Okay. All right. So there's how we do that. That's our second. Those two theorems are really our second way of counting sets. We can do a lot of, we can count a lot of sets with those two ideas. Okay, those two ideas. All right.
Are we turning in our homework?
Sets and algorithms. What?
Are we turning in our
Okay. So, all right. All right. Let's wait till Monday to turn in the homework. I have the solutions posted, but I wanted to go over one of the problems, which I forgot to go over today, okay, and answer other questions. We're going to have to delay the test slightly, but we're in good shape. But we're going to have to delay the test a little bit because I want to make sure that we have covered all of the examples of all of our counting techniques. And I've got the notes written, but we haven't gotten through all the notes yet, okay? So we may have to, we'll have to delay that a little bit. So let's plan on Monday for the homework. So if you have any questions about that, be sure to come by and see me. Oops, we're out of time. Sorry.